There's a photograph that exists somewhere, maybe on a hard drive, maybe in an archive, maybe printed on paper in a filing cabinet in an observatory basement. It's not a famous photograph. You've probably never seen it. Most people haven't. But it's special in a way that's almost impossible to comprehend. It's a photograph of a galaxy, just one galaxy among hundreds of millions we've captured. But here's what makes it extraordinary. That galaxy, that tiny smudge of light in the image, contains somewhere between 100 billion and 1 trillion stars, each one potentially hosting planets, each one a sun to worlds we'll never visit. And that's just one galaxy, one photograph among hundreds of millions. Tonight, I want to take you on a journey through the history of galaxy photography. I want to show you how we went from thinking the Milky Way was the entire universe to having detailed images of hundreds of millions of distant galaxies. I want to explain how astronomers count galaxies, how they estimate the total number in the observable universe, and why we can never photograph them all. And most importantly, I want you to understand what it means that we can do this, that we can point telescopes at the sky and capture light that's been traveling for billions of years, that we can build a photographic catalog of the universe itself. Because when you really think about it, when you grasp what we've accomplished, it's breathtaking. We live on a small planet orbiting an average star in a typical galaxy. And from this vantage point, using instruments we've built with our own hands and minds, we've photographed hundreds of millions of other galaxies. We've documented the universe. We've created a visual record of cosmic structure spanning billions of light years. That's not nothing. That's extraordinary. And the number of galaxies we've photographed, the specific count, tells us something profound about human capability, about the power of technology and curiosity combined, about what's possible when we decide to look up and really see what's out there. So, let me ask you the question that's going to guide our entire conversation tonight. How many galaxies have we actually photographed? Not how many exist, not how many we estimate are out there, but how many have we actually captured in images? How many have we detected, resolved, and recorded? The answer might surprise you. It's both smaller and larger than you'd expect. Smaller because despite all our technology and all our telescopes, we've only photographed a tiny fraction of the galaxies in the observable universe. We've barely scratched the surface. But larger because the number we have photographed is staggering in its own right. It's in the hundreds of millions, maybe approaching a billion, depending on how you count. And each one represents a triumph of observation, of technology, of human persistence in trying to understand the cosmos. But before I give you specific numbers, before we dive into catalogs and surveys and deep fields, I need to make sure we're on the same page about what it means to photograph a galaxy. Because this is more complicated than it sounds. When you photograph something on Earth, a tree or a building or a person, it's straightforward. Light reflects off the object, enters your camera lens, hits the sensor or film, and you have an image. The object is resolved. You can see details. You can make out structure. But galaxies are different. They're incredibly far away. Millions of light years distant in the nearest cases. Billions of light years for most of what we observe. At these distances, even enormous galaxies appear tiny. In many cases, they're not much bigger than a single pixel in an image. So, what counts as photographing a galaxy? If a galaxy appears as a single point of light in an image, indistinguishable from a star, have you photographed it? Most astronomers would say yes, as long as you can confirm it's a galaxy and not a star. Detection counts. Even if you can't resolve structure, even if you can't see spiral arms or the galactic disk, if you've captured light from that galaxy and recorded it, you've photographed it. But there are gradations. There's a difference between detecting a faint smudge that's probably a galaxy and capturing a detailed image where you can see structure, color, individual star-forming regions. Both count as photographs, but they tell you different amounts of information. When surveys catalog galaxies, they're often counting detections, objects in the image that have the right properties to be galaxies. Extended sources, not point sources. Specific colors and brightnesses, objects that fit the expected characteristics of galaxies at various distances. These automated surveys can identify hundreds of thousands or millions of galaxies in a single dataset. Each one detected, recorded, added to the catalog. Each one technically photographed. Then there are targeted observations, where astronomers point a telescope at a specific galaxy they want to study in detail, where they take long exposures to capture faint details, where they use different filters to see different wavelengths of light. These produce what most people would recognize as galaxy photographs, beautiful images showing spiral structure or elliptical symmetry or irregular clumps of stars. These detailed images are rarer. There are maybe hundreds of thousands of galaxies that have been photographed in this detailed way. Enough to see what type of galaxy it is, to classify it, to study its properties. So, when I say we've photographed hundreds of millions of galaxies, I'm including both categories, the detailed images and the survey detections. The beautiful spiral galaxies where you can count the arms and the faint smudges that required sophisticated analysis to even confirm they're galaxies and not something else. All of it counts. All of it contributes to our understanding. All of it represents light that traveled across cosmic distances, entered our telescopes, and was recorded for posterity. Now let me take you back to the beginning, to the first time a human being photographed a galaxy, though they didn't know that's what they were doing at the time. In the late 1800s, astronomy was transitioning from visual observation to photography. For centuries, astronomers had used their eyes, looking through telescopes and drawing what they saw. But photography promised something better: permanence, objectivity, the ability to accumulate light over long exposures and see fainter objects than the eye could detect. And, crucially, the ability to study an image later, to measure precisely, to compare observations from different nights. Astronomers began photographing the night sky systematically: stars, planets, the moon, nebulae, everything they could point their telescopes at. And among the objects they photographed were what they called spiral nebulae, fuzzy patches of light with a distinctive spiral structure. Beautiful, mysterious objects. But what were they? Most astronomers in the late 1800s thought these spiral nebulae were clouds of gas within our own Milky Way galaxy, regions where stars might be forming. Interesting, certainly, but just local objects, part of our cosmic neighborhood. Some people suspected otherwise. Philosophers and a few forward-thinking astronomers proposed that these spiral nebulae might be island universes, separate galaxies like our own, incredibly far away, containing billions of stars. But there was no way to prove it, no way to measure the distance. The debate raged for decades. In 1917, a photograph was taken at Lick Observatory of what was then called the Andromeda Nebula, a large, spiral nebula visible to the naked eye on a dark night. This photograph captured detail that would eventually help resolve the debate. But it wasn't until the early 1920s that the question was finally settled. Edwin Hubble, working at Mount Wilson Observatory with the most powerful telescope of the time, took photographs of the Andromeda Nebula over several nights. And in these photographs, he identified individual stars. Not just the blended light of countless stars appearing as a fuzzy glow, but actual individual points of light that he could track from one night to the next. Some of these stars were variables, Cepheid variables, stars that pulsate regularly, getting brighter and dimmer. And, crucially, the relationship between their pulsation period and their intrinsic brightness was known. By measuring the period, Hubble could determine how bright these stars actually were. By measuring how bright they appeared, he could calculate how far away they must be. And the distance he calculated was staggering, about 900,000 light-years, far beyond the known extent of the Milky Way, which meant the Andromeda Nebula wasn't a nebula at all. It was a galaxy, an island universe, a separate collection of billions of stars at an enormous distance. And if Andromeda was a separate galaxy, then all those other spiral nebulae probably were too. The universe suddenly got much, much bigger. And that photograph, those plates Hubble exposed showing individual Cepheid variables in Andromeda, those were the first true photographs of another galaxy as a galaxy. The first images taken with the understanding of what they were actually showing, not a local cloud of gas, but an entire galaxy, containing as many stars as our own Milky Way, at a distance measured in hundreds of thousands of light-years. That was 1923, just over 100 years ago. Since then, we've photographed hundreds of millions more. But every single galaxy photograph that's come after, every survey image and every deep field and every targeted observation, they all trace their lineage back to that moment, to Hubble's photographs of Andromeda, to the realization that those spiral nebulae were galaxies, to the beginning of extragalactic astronomy. From that point forward, the number of photographed galaxies began to grow, slowly at first. Each photograph required long exposures on photographic plates. Each plate had to be developed, examined, catalogued. The process was labor-intensive, but astronomers were systematic. They photographed the sky methodically, building up a catalogue of galaxies, classifying them into different types, spiral, elliptical, irregular, measuring what they could, positions, brightnesses, sizes. By the mid-20th century, several thousand galaxies had been photographed in detail, enough to begin understanding galaxy populations, enough to see patterns, enough to ask deeper questions about how galaxies form and evolve. Then came the major sky surveys, projects designed to photograph the entire sky, or at least large portions of it, to a uniform depth and quality. These surveys revolutionized how we count galaxies. The first major photographic survey was the Palomar Observatory Sky Survey, completed in the 1950s. Using the 48-inch Schmidt telescope at Palomar Observatory in California, astronomers systematically photographed the northern sky. They divided the sky into overlapping fields. Each field was photographed on a large glass plate using red-sensitive and blue-sensitive emulsions. The result was a complete photographic atlas of the northern sky, showing stars and galaxies down to a certain limiting magnitude. This survey was a monumental undertaking. It took years to complete. The photographs covered about 90% of the entire sky visible from Palomar. And when astronomers began examining these plates, counting and cataloging the objects visible in them, they found galaxies, lots of galaxies. In some fields, hundreds. In others, thousands. The total number of galaxies visible in the Palomar survey was in the millions. Not all of them were individually catalogued. That would have been impossible with the technology of the time. But statistical samples were taken, regions were examined in detail, and astronomers began to understand just how numerous galaxies are, just how densely packed the universe is with these island universes. The Palomar survey plates became a fundamental reference. For decades, if you wanted to know what was in a particular region of the sky, you looked at the Palomar plates. They were the baseline, the foundation on which later observations were built. But the plates had limitations. They were analog. Examining them required physical access. Measuring positions and brightnesses was labor-intensive, done by hand or with mechanical devices, and they captured only visible light, only what human eyes, enhanced by photography and large telescopes, could see. The next revolution came with digital detectors. In the 1980s and 90s, astronomers began replacing photographic plates with CCDs, charge-coupled devices. The same technology used in digital cameras, but optimized for astronomy. CCDs could detect fainter objects than film. They were more sensitive, more linear, and they produced digital data that could be analyzed by computers. This was transformative. Now, surveys could be not just photographic projects, but data generation machines. Every observation produced digital files that could be stored, processed, analyzed by automated software. Galaxies could be identified and catalogued automatically, positions and brightnesses measured precisely. The catalogues could be shared electronically, used by astronomers around the world. And the surveys got bigger, much bigger. The Sloan Digital Sky Survey, SDSS, began in the year 2000. It was designed to photograph about 1/4 of the entire sky using a dedicated 2.5-meter telescope in New Mexico. But unlike previous surveys, SDSS wasn't just taking pictures, it was taking data. Multi-band imaging in 5 different filters, from ultraviolet to near-infrared. Each galaxy detected appeared in 5 images at different wavelengths. And for hundreds of thousands of galaxies, SDSS also obtained spectra, breaking the light into its component wavelengths to measure what elements are present and how fast the galaxy is moving. The amount of data was staggering. Over the course of about a decade of initial operations, SDSS imaged about 1/3 of the sky and detected hundreds of millions of objects, stars, galaxies, quasars. The automated pipeline identified and classified them. The catalog was made publicly available. Any astronomer anywhere could download the data and use it. And the number of galaxies in the SDSS catalog? Over 200 million. 200 million galaxies, each one detected in 5 wavelength bands, each one with a measured position, brightness, size, color, many with spectra, many with distance estimates. 200 million galaxies photographed and catalogued by a single survey. That's transformative. That's a complete game changer for how we understand galaxy populations. But SDSS was operating in visible light. What about other wavelengths? Galaxies emit light across the electromagnetic spectrum: infrared, ultraviolet, radio waves, X-rays. Each wavelength reveals different information. Infrared shows you cool dust and old stars. Ultraviolet shows you hot young stars. Radio waves show you magnetic fields and cold gas. To get a complete picture, you need to observe across the spectrum. The 2-micron All-Sky Survey 2-mass operated from 1997 to 2001. It photographed the entire sky in near-infrared light, wavelengths just beyond what the human eye can see. Infrared is important because it penetrates dust. Visible light gets absorbed and scattered by dust in our galaxy and in distant galaxies. But infrared passes through. This means 2-mass could see galaxies that were obscured in visible light, galaxies behind dusty regions of the Milky Way, galaxies whose own dust was hiding their stars. The survey detected and catalogued over 1 million galaxies. Not as many as SDSS, but these were galaxies that complemented the visible light catalogues. Some were in the SDSS catalog too, now observed at a different wavelength. Others were new detections, galaxies too dust-obscured to show up in visible light surveys, adding another million to the total count. Then there's PanSTARRS, the Panoramic Survey Telescope and Rapid Response System. Operating from Hawaii, PanSTARRS has been surveying the sky since 2008. It's designed for wide-field imaging, capturing large areas of sky in each exposure. Over the years, PanSTARRS has detected and catalogued about 3 billion objects. Not all of them are galaxies. Many are stars, but hundreds of millions are galaxies. The exact number depends on how you classify objects, what thresholds you use, but conservative estimates put it at several 100 million galaxies. Again, each one detected, measured, catalogued. Each one added to our photographic record. Are you starting to see the picture? Each major survey adds tens or hundreds of millions of galaxies to the total count. SDSS, 2-mass, PanSTARRS, and several others I haven't mentioned. European surveys, Australian surveys, surveys from telescopes in Chile and South Africa and China, all contributing, all photographing different parts of the sky, or the same parts at different wavelengths or different depths. And the numbers add up. When you combine all these surveys, when you account for overlaps where the same galaxy appears in multiple catalogues, when you include both wide field surveys that cover huge areas shallowly and deep surveys that look at small areas but see very faint galaxies, you get a total that's in the hundreds of millions. Maybe approaching a billion, depending on exactly what you count and how you define photographed. But I want to make sure you understand what these numbers mean, because it's easy to hear hundreds of millions and have it just wash over you as a big number. Let me put it in perspective. Every galaxy we've photographed required light to travel from that galaxy to Earth. For nearby galaxies like Andromeda, that's about 2.5 million years. The light left Andromeda when our ancestors were still learning to use stone tools, and it arrived at our telescopes in the last century. For distant galaxies visible in deep surveys, the light has been traveling for billions of years. It left those galaxies when the universe was young, when our sun didn't exist, when the Milky Way looked completely different. And that light, after traveling across billions of light years, entered our telescopes, hit our detectors, was recorded. Each photon that struck the detector came from a star in that distant galaxy, a star that might no longer exist, that might have died billions of years ago, but its light kept traveling, kept moving through the expanding universe until finally it reached Earth and contributed to an image. Hundreds of millions of galaxies means hundreds of millions of times this happened. Hundreds of millions of instances where we captured light from distant collections of billions of stars, documented their existence, added them to our catalogue of cosmic structure. Now let me tell you about a different kind of galaxy photography. Not surveys trying to cover as much sky as possible, but deep field observations. Pointing a telescope at a tiny patch of sky and staring at it for a very long time, accumulating light, seeing incredibly faint, incredibly distant objects that wouldn't show up in shallower surveys. The most famous example is the Hubble Deep Field. In 1995, astronomers proposed using the Hubble Space Telescope to do something that seemed crazy. They wanted to point it at an apparently empty patch of sky, a region where there were no bright stars, no obvious galaxies, just darkness. And they wanted to stare at this nothing for 10 days. 10 days of Hubble's precious time focused on apparent emptiness. Some people thought it was a waste, but the astronomers had a good reason. They knew that even in apparently empty regions, there should be distant galaxies, so faint and so far away that they'd never been seen before. And if Hubble stared long enough, accumulated enough light, those galaxies would appear. They were right. The Hubble Deep Field image, released in January 1996, was stunning. In that tiny patch of sky, about the size of a grain of sand held at arm's length, Hubble detected about 3,000 galaxies. 3,000 galaxies in a patch of sky that appeared empty to every previous observation. Galaxies at various distances, some relatively nearby, showing clear spiral or elliptical structure. Others incredibly far away, so distant that they appeared as they were billions of years ago when the universe was young. The Hubble Deep Field changed how we think about galaxy density. It showed that galaxies are everywhere, that even in the darkest, emptiest-looking regions of sky, there are thousands of galaxies if you look deep enough. And it allowed astronomers to do something remarkable. They could extrapolate. If there are 3,000 galaxies in this tiny patch of sky, and the universe is roughly uniform on large scales, then we can estimate how many galaxies exist in the entire observable universe. The calculation gave numbers in the hundreds of billions, later refined to about 2 trillion galaxies in the observable universe. But here's the thing. The Hubble Deep Field itself only photographed 3,000 galaxies. In subsequent years, Hubble did similar observations in other patches of sky. The Hubble Ultra Deep Field, staring at an even smaller region for even longer, detected about 10,000 galaxies. Other deep fields were added, but even combining all the deep field observations, we're talking about tens of thousands of galaxies. A tiny fraction of the total in the universe, a tiny fraction even of what surveys have catalogued. So why are deep fields important? Because they reach farther, they see fainter, they detect galaxies that wouldn't appear in any survey, and they provide the calibration we need to estimate the total galaxy population. They tell us how many galaxies we're missing, how many exist but are too faint or too distant for our current surveys to detect. Without deep fields, we wouldn't know that there are about 2 trillion galaxies in the observable universe. We'd only know about the hundreds of millions we've detected in surveys. The deep fields show us what we're missing. They're like drilling a core sample in the ocean. You're only sampling a tiny area, but if you go deep enough, you learn about layers and depths that you couldn't access by skimming the surface. The Hubble Deep Field and its successors are core samples of the universe, showing us the full depth of galaxy populations, revealing the faint and distant galaxies that fill space but are invisible to shallower observations. And every galaxy in those deep fields has been photographed, captured in exquisite detail, available for study, added to our total count. So, let me start giving you some concrete numbers. Let me try to sum up what we've actually photographed. The Sloan Digital Sky Survey catalogued about 200 million galaxies. Pan-STARRS has catalogued several hundred million, with significant overlap with SDSS, but also many new detections. 2MASS added about 1 million in the near-infrared, many of them unique to that wavelength. Other surveys, European Southern Observatory surveys, Australian surveys, the UKERT Infrared Deep Sky Survey, the VISTA surveys, and dozens of smaller projects collectively add tens of millions more. When you try to combine all these catalogues, accounting for the fact that the same galaxy might appear in multiple surveys, you get a total somewhere in the range of 500 million to potentially approaching 1 billion individual galaxies that have been detected and catalogued. That's the number that have been photographed in surveys, detected as extended sources, classified as galaxies, had their positions and properties measured. 500 million to 1 billion galaxies. Now add the targeted observations. Galaxies that astronomers have specifically chosen to study in detail. Major galaxies like Andromeda, the Whirlpool Galaxy, the Sombrero Galaxy, all the named and famous galaxies you might have seen pictures of. There are thousands of these. Tens of thousands probably, if you include every galaxy that's been the subject of a detailed observational study. Each one photographed, often multiple times, at multiple wavelengths by multiple telescopes. These targeted observations don't significantly change the total count because most of these galaxies are also in the survey catalogues. But they add depth, they add detail, they transform catalog entries into rich datasets that tell us about the galaxy's structure, composition, history. Then there are the deep fields. Hubble's various deep field observations have photographed perhaps 50,000 galaxies total, combining all the different deep field campaigns. The James Webb Space Telescope, which started operations in 2022, has already contributed several new deep field images, adding thousands more faint distant galaxies. And other telescopes have done their own deep field observations. Every one of those is a galaxy that's been photographed, many of them so distant and faint that they appear in no catalogue except the specific deep field study that found them. So, what's the total? If I had to give you a single number, if I had to estimate how many galaxies we've actually photographed, I'd say between 500 million and 1 billion. That's my best estimate based on combining all the major surveys, accounting for overlaps, including deep fields and targeted observations. Somewhere in that range. We've photographed somewhere between 500 million and 1 billion galaxies. Let that sink in for a moment. 1 billion galaxies. Each one a collection of billions or trillions of stars. Each one potentially hosting trillions of planets. Each one a universe unto itself, full of complexity and structure and history. And we've photographed 1 billion of them. We've captured their light, documented their existence, created a photographic record that will persist as long as human civilization does. That's extraordinary. That's an achievement that would have been unimaginable just a century ago when we didn't even know for certain that galaxies beyond our own existed. But here's the sobering part. That 1 billion galaxies we've photographed, it's a tiny fraction of the total. Remember that estimate of 2 trillion galaxies in the observable universe? We've photographed maybe 1/20th of 1%, maybe 0.05% of all galaxies. The vast majority remain unphotographed, too faint, too distant, too obscured by dust or hidden behind brighter objects. We've barely scratched the surface, and yet that tiny fraction we have photographed is enough to revolutionize our understanding of the universe. It's enough to map large-scale structure, to trace the cosmic web of galaxies, to study how galaxies form and evolve over cosmic time, to understand the role of dark matter and dark energy in shaping cosmic structure. 1 billion galaxies is enough to do cosmology, to probe the nature of the universe itself. But it's nowhere near all of them. There are trillions more out there waiting to be photographed, and we're working on it. Let me tell you what we learn from each galaxy photograph, because these aren't just pretty pictures. Each one is data. Each one tells us something. Start with the basics. When you photograph a galaxy, you can classify it. Is it a spiral galaxy with elegant arms wrapping around a central bulge? Is it an elliptical galaxy, a smooth oval blob of stars with no clear structure? Is it irregular, a chaotic mess of stars with no symmetry? This classification tells you about the galaxy's history. Spirals are typically younger galaxies with active star formation happening in their arms. Ellipticals are older, filled with ancient stars, no longer forming new ones. Irregulars might be galaxies that have been disrupted by collisions or that never settled into a regular structure. From a single image, you can estimate how many stars the galaxy contains. Brighter galaxies have more stars. The total luminosity gives you the stellar mass, at least approximately. You can also estimate the size, how big the galaxy is in physical space. Combined with the brightness, this tells you about the galaxy's density. Some galaxies are compact, with lots of stars packed into a small space. Others are diffuse, spreading their stars over larger volumes. If you photograph a galaxy at multiple wavelengths, you learn even more. Blue light comes from hot young stars. Red light comes from cool old stars. A galaxy that's very blue is actively forming stars. A galaxy that's very red is dominated by old stellar populations, no longer making new stars. Infrared observations show you dust. Where is dust concentrated? How much is there? Dust is important because it's where stars form. Dense clouds of dust and gas collapse to birth new stars. So, a galaxy rich in dust is potentially a galaxy with active star formation. You can also measure the galaxy's distance, though this requires more than just a photograph. You need a spectrum, breaking the light into wavelengths, to measure the redshift. How much the light has been stretched by the expansion of the universe. Greater redshift means greater distance. Once you know the distance, you know when the light left the galaxy. You're seeing the galaxy as it was millions or billions of years ago. For distant galaxies, you're looking back in time. You're seeing what galaxies looked like in the early universe. This is how we study galaxy evolution. By photographing galaxies at various distances, we see them at various cosmic epochs. We can watch how galaxy properties change over billions of years, how spirals evolve into ellipticals, how galaxies grow through mergers, how star formation has declined over cosmic history. Every galaxy photograph is a snapshot of a moment in that galaxy's history, a frozen instant in a billions of years long story. And by collecting millions or billions of these snapshots at different distances, different times, we reconstruct the full narrative. We see how galaxies form, grow, change, and age over the entire history of the universe. Photographs also let you find rare and unusual objects. Most galaxies are ordinary, spirals or ellipticals of typical sizes and brightnesses. But occasionally you find something weird, a galaxy with a strange shape, a ring galaxy, circular with a hole in the middle, formed by a head-on collision with another galaxy, a polar ring galaxy, with one disk of stars orbiting perpendicular to another. An ultra-compact dwarf galaxy, tiny but extremely dense. A galaxy with an active nucleus powered by a supermassive black hole consuming material. These unusual galaxies teach us about processes that don't happen often but are important. Collisions and mergers, black hole growth, extreme environments. By photographing millions of galaxies, you increase your odds of finding these rare specimens. They're needles in haystacks, but if you photograph enough haystacks, you'll find enough needles to study them. There are also personal stories, individual galaxies that have taught us something profound or that marked a turning point in our understanding. Galaxies that were photographed at just the right time, in just the right way, to reveal something unexpected. Let me give you an example. The Tadpole Galaxy, also called UGC 124. It was photographed by the Hubble Space Telescope in 2002 as part of an observing program studying interacting galaxies. The image showed something extraordinary. The galaxy has a long tail of stars stretching out behind it, over 250,000 light-years long. A tail that looks like a tadpole, hence the name. What created this tail? Gravitational interaction with another galaxy. The tadpole passed close to a smaller galaxy, visible in the Hubble image. The tidal forces from that close encounter pulled stars out of the tadpole's disk, creating the tail. Over time, those stars will spread out and disperse. The tail is temporary, a fleeting structure that will last only a few 100 million years before fading. But Hubble caught it at just the right moment. We have a photograph of this galaxy during this dramatic event in its history. That image has been studied extensively. It's taught us about galaxy interactions, about tidal tails, about how collisions and close encounters reshape galaxies. And it all comes from one photograph, one observation at the right time. Multiply that by hundreds of millions. Every galaxy we've photographed has a story. Most are ordinary stories. A typical spiral doing typical spiral things, forming stars in its arms, rotating around its center, slowly consuming its gas and evolving over billions of years. But some are extraordinary. Some capture rare events. Some show us things we didn't know were possible. And we don't know which ones will be important until we look, until we photograph them and study the images. That's why surveys are so valuable. By photographing millions of galaxies systematically, you ensure that you'll catch the rare and unusual ones. You'll find the weirdos, the outliers, the galaxies that are doing something different from all the rest. And those are often the ones that teach us the most. Let me also tell you what we don't learn from galaxy photographs, at least not from a single image. You can't see individual stars in distant galaxies. They're too far away. Even the largest, brightest stars become invisible beyond a few 100 million light-years. So, when you photograph a distant galaxy, you're seeing the blended light of billions of stars. You can infer properties. Colors tell you about stellar populations. Bright regions might be star-forming areas. But you're not resolving individual stars. You're seeing the galaxy as a whole. You also can't see planets. No telescope we currently have can photograph a planet in another galaxy. The light from a planet is so much fainter than the light from its star, and both are so far away that distinguishing the planet is impossible. We can barely photograph planets around stars in our own galaxy. Planets in other galaxies are completely beyond our reach. You can't see what's inside galaxies. The dense molecular clouds where stars form, the supermassive black holes at galactic centers, the dark matter halos that surround galaxies. All of this exists, we know from indirect evidence, but you can't photograph it directly, at least not with visible light. Radio observations can show you the molecular clouds, X-ray observations can reveal the hot gas near supermassive black holes. But a standard photograph in visible light shows you stars. Just stars. Billions of them blended together. And you can't see the history. You can't see what the galaxy looked like a billion years ago, or what it will look like a billion years in the future. You're seeing a single moment, a snapshot. To understand the full story, you need multiple galaxies at different distances, different times. You need to piece together the narrative from many snapshots. So, galaxy photographs are powerful but limited. They tell you a lot, but not everything. They're the starting point, not the ending point. They show you what and where. But to understand why and how, you need more observations, more data, spectra, multi-wavelength imaging, detailed follow-up studies. The photograph gets you interested, gets you asking questions, but answering those questions requires going deeper. This is why astronomy is never done, why we keep building bigger telescopes, more sensitive detectors, more sophisticated instruments. Every observation raises new questions. Every galaxy photographed reveals mysteries that need new observations to solve. It's a beautiful, endless cycle of discovery. And we're living in the golden age of it. Right now, as you're listening to this, there are telescopes all over the world and in space photographing galaxies, adding to the catalogue, capturing light from distant island universes. The numbers I've given you, the hundreds of millions or approaching a billion, those are current as of now. But tomorrow, next week, next month, those numbers will be higher. More surveys are running. More observations are being made. More galaxies are being added to the total. The catalogue is always growing, always expanding. We'll never photograph all the galaxies. There are too many. But we can keep adding to our collection. Keep pushing deeper and farther. Keep capturing more of the cosmic population. And every addition matters. Every new galaxy photographed is another piece of the puzzle, another data point in our understanding of cosmic structure and evolution. It's worth appreciating what this represents. This photographic catalogue we've built of hundreds of millions of galaxies. It's a record of the universe, a visual documentation of cosmic structure at a particular moment in time. Billions of years from now, these photographs will still exist, assuming human civilization preserves them. Future beings will be able to look back and see what the universe looked like in our epoch. They'll see the galaxies we saw, captured in images we made. Just as we can look at Hubble's photographs of Andromeda from the 1920s and see what he saw, what the universe looked like then, future astronomers will look at our Hubble images, our survey data, our catalogues, and see what we saw, what we recorded. We're creating a time capsule, a photographic record that will outlast us. That's meaningful. That's worth doing. And it's one more reason why each galaxy photograph matters, why the total count matters, why this entire endeavor of systematically documenting the universe through photography is one of humanity's great achievements. I want to make sure you understand just how revolutionary this is in historical terms. For most of human history, we couldn't photograph anything. Photography was invented in the 1800s. Before that, if you wanted a record of what something looked like, you had to draw it, sketch it, paint it. This worked fine for nearby objects, but for astronomy, for documenting faint, distant objects visible only through telescopes? It was inadequate. Drawings were subjective. Different observers saw different details, made different interpretations. There was no objective record. Then photography came along, and everything changed. Suddenly, you could capture exactly what the telescope saw. No interpretation, no artistic license, just the light itself, recorded permanently. This was transformative for astronomy, but even early photography had severe limitations. Long exposures were required to capture faint objects. Photographic plates were not very sensitive. You needed huge telescopes and hours of exposure time to photograph anything beyond the brightest objects. In the early 1900s, photographing galaxies required dedicated effort. You had to choose your target carefully, set up the telescope, guide it precisely to compensate for Earth's rotation, expose a plate for hours, develop it, examine it under magnification. It was painstaking work, and the results, by modern standards, were crude, fuzzy images with limited detail. But they were revolutionary at the time. They showed that these nebulae existed, that they had structure, that they could be studied. As technology improved, as telescopes got bigger, as photographic emulsions got more sensitive, the quality and quantity of galaxy photographs increased. By mid-20th century, with surveys like Palomar, we were systematically photographing thousands of galaxies. By the late 20th century, with digital detectors, we were cataloging millions. And now, in the early 21st century, we're approaching 1 billion. That exponential growth reflects technological progress. Better telescopes, better detectors, better data processing. But it also reflects commitment. Generations of astronomers dedicating their careers to this work, building the instruments, conducting the surveys, analyzing the data, creating the catalogs. It's a collective human achievement. No single person photographed hundreds of millions of galaxies. It took thousands of people over more than a century, engineers who built the telescopes, astronomers who designed the surveys, programmers who wrote the software to process the data, technicians who maintained the instruments, funding agencies that paid for it all, taxpayers who supported the funding. It's a testament to what we can accomplish when we work together toward a common goal, when we decide that understanding the universe is worth the effort and resources. And the result is this incredible catalog, this photographic record of hundreds of millions of galaxies, available to anyone who wants to study it. Open data, in many cases, freely accessible to astronomers around the world, to students, to anyone curious enough to download and explore. That's powerful. That's democratizing. That's what science should be. Not hidden knowledge, but shared understanding. Not proprietary data, but common heritage. The galaxies we photographed belong to all of us. The catalog we've built is humanity's catalog, not any individuals or nations. It's our collective record of the universe we inhabit, and it's growing. Right now, there are surveys underway that will add hundreds of millions more galaxies in the coming years. The Vera Rubin Observatory, currently under construction in Chile, will begin operation soon. It's designed to photograph the entire southern sky repeatedly, detecting faint, distant objects and tracking how they change over time. The survey will detect billions of objects, many of them galaxies, potentially doubling or tripling the number of catalogued galaxies over the next decade. That's what's coming. That's the near future. But before we get to the future, before we talk about what's next, I want to make sure you've really grasped the magnitude of what we've already accomplished. Hundreds of millions of galaxies photographed, each one captured in digital data, each one studied, at least briefly, each one adding to our understanding. That's where we are. That's what humanity has achieved through telescopes and cameras and persistence. It's extraordinary. And it's just the beginning. Let me take a moment to answer a question you might be having. Why does it matter how many galaxies we've photographed? Why does the specific count matter? Does it change anything? Whether it's 500 million or a billion, in some sense, no. The science doesn't fundamentally change based on whether we've catalogued 500 million or a full billion galaxies. We've photographed more than enough to do meaningful cosmology, to study galaxy populations, to understand cosmic structure. The marginal value of each additional galaxy decreases as the total climbs. But in another sense, yes, it matters a lot. The count reflects our capability. It shows what we can do, what we've achieved. A century ago, we'd photographed maybe a few dozen galaxies in detail. Now it's hundreds of millions. That progression, that exponential growth, shows human progress, shows technological advancement, shows what happens when we invest in scientific infrastructure. The count also matters because of what we're missing. Knowing that we've photographed maybe 0.05% of all galaxies tells us how much more there is to discover, how much we don't know. It keeps us humble, reminds us that our knowledge is incomplete, that there are trillions of galaxies out there we've never seen, that the universe is larger and more complex than our catalogues can capture. And the count matters because every galaxy represents potential. Potential for discovery. Potential for understanding. We don't know which galaxies will be important, which ones will teach us something profound. So we photograph as many as we can, catalog as many as we can, make the data available to as many people as we can, and let the scientific community dig through it, asking questions, finding patterns, making discoveries. Some of the most important findings in modern astronomy have come from mining these large catalogues, from asking questions that require statistical samples of thousands or millions of galaxies, questions about how galaxy properties correlate, how they depend on environment or cosmic epoch, how rare events are distributed across galaxy populations. You can't answer these questions with a handful of galaxies. You need large numbers. You need comprehensive catalogues. And that's what we've built. That's what these hundreds of millions of photographed galaxies give us. The ability to do statistical cosmology, to study galaxies not just as individual objects, but as populations, to see the forest, not just the trees. So, yes, the count matters. The specific number matters. Whether it's 500 million or a billion, whether we're photographing 1,000% or 100% of all galaxies, it matters. Because each galaxy adds to our understanding. Each photograph contributes to the catalogue. Each observation brings us closer to comprehending the cosmos. And we're not done. We're nowhere near done. The hundreds of millions we've photographed are a foundation, a starting point. The next generation of surveys will add hundreds of millions more. Eventually, maybe, we'll approach photographing 1% of all galaxies. then 2%. Maybe centuries from now, with telescopes we can't imagine, we'll photograph 10%, 20%. We'll never photograph them all. There are too many, spread across too vast a volume, many too distant to ever be seen, no matter how good our telescopes become, because their light hasn't had time to reach us yet. But we can keep pushing, keep adding to the catalogue, keep photographing more of the cosmic population. And every addition is valuable. Every new galaxy captured is worth the effort, because this is how we understand the universe, by looking, by observing, by photographing everything we can see and studying the images until they reveal their secrets. That's astronomy. That's what we do. And the catalogue of hundreds of millions of galaxies we've already photographed is proof that it works. Proof that this approach, this patient, systematic documentation of the cosmos, leads to understanding, leads to knowledge, leads to a deeper appreciation of our place in this vast, ancient, beautiful universe. So, when someone asks how many galaxies we've photographed, the answer is hundreds of millions, approaching 1 billion. And that answer should fill you with wonder, should make you appreciate human capability, should remind you that we're living in an age of cosmic discovery, an age when we can capture light from billions of light years away and use it to understand the structure and history of the universe itself. That's extraordinary. That's the world we live in. That's the privilege we have. And understanding these numbers, understanding what they represent, makes you part of this grand endeavor, makes you part of humanity's quest to photograph and understand the cosmos. I'm going to keep going because there's so much more to explore. We need to talk about what it takes to photograph a galaxy, the technical challenges, the limitations of our current technology. What prevents us from photographing more? We need to talk about the future, about upcoming telescopes and surveys that will dramatically increase our count, about what we'll discover when we push deeper and see fainter galaxies. And we need to talk about what it all means, what these photographs represent, why they matter, how they change our perspective on existence itself. So stay with me. We're only halfway through this journey. There's still so much to understand about how we photograph galaxies, what we learn from those photographs, and why this entire endeavor matters so profoundly. The answer to how many galaxies we've photographed is beginning to crystallize. It's in the hundreds of millions. It's a tiny fraction of the total, but an enormous achievement in its own right. And understanding that number, understanding where it comes from and what it represents, is understanding one of humanity's greatest accomplishments: the systematic photographic documentation of the universe itself. Let me take you deeper into what it actually means to photograph a galaxy at the technical level. Because I think when you understand the challenges, when you grasp how difficult this is, it makes the achievement even more remarkable. A galaxy is faint, incredibly faint. Even nearby galaxies like Andromeda, which you can see with the naked eye on a dark night, are dim compared to bright stars. And Andromeda is one of the brightest galaxies in the sky. Most galaxies are far fainter, so faint that even looking through a large telescope, your eye wouldn't see them. They require long exposures, minutes or hours of accumulated light before enough photons have hit the detector to form an image. This is fundamentally different from photographing objects on Earth. When you take a picture of a person or a landscape, light from the sun reflects off those objects and floods your camera sensor. You need a fast shutter speed to avoid overexposing, but with Galaxies, you're dealing with objects that are inherently dim and incredibly far away. Every photon counts, and getting enough photons to form a detailed image requires patience and precision. Modern digital detectors help enormously. They're sensitive enough to register individual photons. They can accumulate signal over long exposures without the noise problems that plagued photographic film. But even with the best detectors, photographing faint galaxies requires significant telescope time, and telescope time is precious. Every major observatory has far more proposals for observations than they can possibly accommodate. Deciding which galaxies to photograph, which surveys to conduct, requires careful prioritization. Then there's atmospheric interference. Earth's atmosphere is constantly moving, turbulent, distorting the light that passes through it. This is why stars twinkle. The atmosphere bends the light slightly, causing the star's position to shift rapidly. For human eyes, this creates a pleasant twinkling effect. For astronomers trying to take sharp images, it's a nightmare. Atmospheric turbulence limits the resolution of ground-based telescopes. No matter how big your telescope is, no matter how perfect your optics, the atmosphere blurs the image. This effect, called seeing, varies with location and time. Some nights are better than others. Some locations have steadier atmospheres. This is why major observatories are built on mountaintops in remote locations. High altitude means there's less atmosphere above you. Remote locations mean less light pollution and often better seeing. Places like Mauna Kea in Hawaii, the Atacama Desert in Chile, the Canary Islands off Africa. These aren't chosen randomly. They're chosen because they have the best atmospheric conditions for astronomy. But even from these premier sites, atmospheric blurring limits what you can see. Structures smaller than about 1 arcsecond are difficult to resolve from the ground. For comparison, 1 arcsecond is about the angle subtended by a coin viewed from 2 kilometers away. It's tiny, but astronomical objects can have structures much smaller than that. Fine details in galaxies, small features, all get blurred by the atmosphere. This is one reason space telescopes like Hubble are so valuable. Above the atmosphere, there's no turbulence, no blurring. Images can be much sharper. Hubble's resolution is about 0.05 arcseconds, about 20 times better than ground-based telescopes typically achieve. This allows Hubble to see fine details in galaxies that ground-based telescopes can't resolve. It's why so many of the beautiful, detailed galaxy images you've seen come from Hubble. They're not just pretty. They're scientifically valuable because they show structure that other telescopes can't capture. But space telescopes are expensive and rare. We have only a handful operating at any given time, and they can't cover the entire sky the way ground-based surveys can. So we need both. Ground-based telescopes for wide-area surveys covering huge swaths of sky, detecting millions of galaxies. Space telescopes for detailed follow-up, studying individual galaxies with exquisite resolution, seeing fine structures. The combination gives us both breadth and depth. Another challenge is data storage and processing. Every time a survey telescope takes an image, it generates enormous amounts of data. A single wide-field image from a modern survey telescope might be several gigabytes. A night of observing might produce hundreds of gigabytes. A full survey running for years produces petabytes. That's millions of gigabytes. Storing this data requires massive server farms. Processing it requires sophisticated software and powerful computers. When the Sloan Digital Sky Survey began operations, one of the challenges wasn't just taking the images, but managing the data they produced. They had to develop new software pipelines to automatically process each image, identify objects, classify them, measure their properties, and add them to the catalog. This was pioneering work. Before SDSS, most astronomy data was processed manually or semi-manually. Astronomers would examine images by eye, mark objects, measure them with specialized tools. It was labor-intensive and limited how much data you could handle. SDSS changed that. They built automated pipelines that could process images without human intervention. Software would identify objects based on specific criteria, distinguish stars from galaxies based on their appearance, measure brightnesses, colors, sizes, all automatically. This allowed them to handle the huge data volumes the survey produced, and it set the template for future surveys. Now, automated processing is standard. Modern surveys generate so much data that manual processing would be impossible. The computers do the initial work, creating catalogs. Then astronomers query those catalogs, asking questions, looking for interesting objects. But even with automation, the sheer volume is challenging. The upcoming Legacy survey of space and time at the Vera Rubin Observatory will generate about 20 terabytes of data every night. Over 10 years of operations, that's about 60 petabytes total. Storing, processing, and making that data accessible to the global astronomy community requires significant infrastructure. Dedicated data centers, high-speed networks, cloud computing resources. It's not just about building a telescope anymore. It's about building the entire data ecosystem around it. And all of this is necessary to photograph galaxies at scale, to go from the hundreds of thousands catalogued by Palomar to the hundreds of millions we have now. The technology advances, the techniques improve, and the numbers keep growing. But there's a fundamental limit we can't overcome. Distance. The universe is about 13.8 billion years old. Light travels at a finite speed, so there's a maximum distance we can see, called the cosmic horizon. It's determined by how far light could have traveled since the Big Bang. Beyond this horizon, light hasn't had time to reach us yet. We can never see those regions no matter how good our telescopes become. Within the observable universe, the volume we can potentially see, there are an estimated 2 trillion galaxies. But most of them are too faint and too distant for our current telescopes to detect. They exist. Light from them is reaching Earth, but that light is so dim, spread across such a small angle on the sky, that it doesn't register on our detectors. We need bigger telescopes, more sensitive instruments, longer exposures to see them, and even then, The most distant galaxies are at the edge of what's physically possible to observe. Their light has been traveling for over 13 billion years. It's been stretched by the expansion of the universe, redshifted into the infrared, and it's incredibly faint. Only the most powerful telescopes can see them at all. This is where space telescopes like James Webb come in. Webb observes in the infrared, specifically designed to see these ultra-distant galaxies. Its mirror is 6.5 meters across, much larger than Hubble's 2.4 meters. And it's optimized for infrared wavelengths where the most distant galaxies appear. Since beginning operations in 2022, Webb has already detected some of the most distant galaxies ever seen. Galaxies that formed just a few 100 million years after the Big Bang. Galaxies that show us what the early universe looked like. Each one is a precious data point, a window into cosmic history, and each one adds to our total count of photographed galaxies. Now, let me tell you about some of the specific programs and missions that have contributed most significantly to our galaxy count. Start with the Hubble Space Telescope, because even though I've mentioned it several times, I haven't fully conveyed how important it's been. Hubble launched in 1990 and has been operating for over 3 decades. In that time, it's photographed tens of thousands of galaxies in detail. The deep fields alone account for tens of thousands. But beyond the deep fields, Hubble has conducted numerous surveys and targeted observations. The Cosmos Survey, covering 2 square degrees of sky with Hubble's advanced camera for surveys, detected about 2 million objects, many of them galaxies. The Candles Survey, designed to study galaxy formation and evolution, imaged over 250,000 galaxies. The Frontier Fields program focused on galaxy clusters using gravitational lensing to see extremely distant background galaxies. These observations added thousands more faint galaxies to the catalogue. Hubble has also been used for targeted studies of specific galaxies, nearby galaxies where its resolution could reveal fine details. The structure of spiral arms, individual star-forming regions, the properties of galactic centers. These detailed observations of individual galaxies have been combined into large catalogues. The Hubble Legacy Field, released in 2019, combines data from multiple surveys into a single mosaic covering about the same area as the full moon. In that area, about 265,000 galaxies are visible. That's one image, albeit built from thousands of individual exposures, but it shows you the power of deep imaging. In an area smaller than the full moon, there are over 250,000 galaxies. Scale that up to the entire sky. Account for the fact that this is much deeper than most surveys, and you get a sense of how many galaxies there really are out there. Then there's the Spitzer Space Telescope, which operated from 2003 to 2020. Spitzer observed in the infrared, complementing Hubble's visible and near-infrared observations. Infrared is crucial for understanding galaxies because it penetrates dust and reveals cooler components. Old stars, dusty star-forming regions, material near galactic centers. Spitzer conducted several major surveys. The Spitzer Wide, area infrared extragalactic survey covered about 49 square degrees and detected over 2 million galaxies. The Cosmos Spitzer survey added infrared data for the same field Hubble observed, providing multi-wavelength coverage. All of these galaxies detected in infrared by Spitzer add to the total count. Many were also seen by Hubble or ground-based telescopes, but some were only visible in infrared, hidden by dust at visible wavelengths. So Spitzer added unique detections, expanding our catalogue of observed galaxies. James Webb is continuing this legacy. Since starting operations in 2022, Webb has been taking the deepest infrared images ever obtained. The first deep field, released as Webb's first public image, showed a galaxy cluster with hundreds of background galaxies visible through gravitational lensing. Many of these galaxies are so distant and faint that they've never been seen before. Webb is specifically designed to study the early universe, to see the first galaxies that formed after the Big Bang. And it's succeeding. In its first year of operations, Webb has already detected galaxies at redshifts over 13, meaning we're seeing them as they were less than 400 million years after the Big Bang. These are some of the earliest galaxies ever observed. Each one adds to our catalogue of photographed galaxies. But these aren't just detections. These are detailed images. Webb's resolution and sensitivity allow it to see structure in these distant galaxies. We can study their shapes, their sizes, their colors. We can begin to understand what the first galaxies looked like and how they compare to galaxies today. This is frontier science. This is observational cosmology at its best, using the most advanced instruments we have to push the boundaries of knowledge, to see farther and fainter than ever before. And every galaxy Webb photographs adds to humanity's catalogue, adds to the photographic record we're building. Now, beyond NASA missions, there are major contributions from European and other international facilities. The European Southern Observatory operates several world-class telescopes in Chile. The Very Large Telescope, consisting of 4 8-meter telescopes that can be combined, has conducted numerous galaxy surveys. The VMOS survey covered 4 square degrees and detected about 100,000 galaxies with spectroscopy. The KMOS survey studied star formation in distant galaxies, observing thousands. The survey telescope at ESO, called VST, has conducted wide-field surveys like KIDS, the Kilo Degree Survey, which has catalogued millions of galaxies. The Australian astronomical community has contributed through facilities like the Anglo-Australian Telescope. Surveys like the 2-degree Field Galaxy Redshift Survey obtained spectra for over 220,000 galaxies, providing distances and velocity information. This was crucial for mapping large-scale structure in the universe. Then there's the Infrared Space Telescope, WISE, the Wide Field Infrared Survey Explorer. WISE surveyed the entire sky in the mid-infrared from 2010 to 2011. It detected hundreds of millions of objects, many of them galaxies. The All-WISE catalogue contains about 750 million objects. Not all are galaxies, but a significant fraction are. The exact number depends on classification, but conservative estimates suggest at least 100 million galaxies in the WISE data. That's another 100 million photographed galaxies, detected in infrared wavelengths that complement visible and near-infrared surveys. And there are dozens of smaller surveys and programs I haven't mentioned. University-run telescopes conducting targeted surveys, legacy programs on major telescopes, follow-up observations of interesting objects. All of these contribute. All add galaxies to the total count. When you sum everything, when you combine all the major surveys and space missions and targeted programs accounting for overlaps where the same galaxy appears in multiple catalogs, you get that total we discussed earlier. Somewhere between 500 million and approaching 1 billion individually detected and catalogued galaxies. That's our current achievement. That's what humanity has photographed. But I want to emphasize something important. This number is always growing. Every night, somewhere in the world, telescopes are observing, surveys are running, data is being collected, the catalogs are being updated, the count increases continuously. By the time you're listening to this, the number is higher than what I've quoted. Maybe only slightly higher, maybe significantly higher, depending on how much time has passed and what new surveys have completed, but definitely higher. The photographic catalogue of the universe is a living document. It's never finished. It's always expanding, and in the near future, it's going to expand dramatically. Let me tell you about what's coming. The Vera Rubin Observatory, currently under construction in Chile, is going to revolutionize wide-field astronomy. It features an 8.4-meter primary mirror and an enormous camera, the largest digital camera ever built for astronomy, 3.2 gigapixels. That's 3,200 megapixels. Each image will cover an area of sky about the size of 40 full moons. The survey it will conduct, called the Legacy Survey of Space and Time, or LSST, will photograph the entire visible sky from Chile every few nights. It will run for 10 years, taking millions of images, detecting billions of objects. Current estimates suggest LSST will catalogue about 20 billion galaxies. That's not a typo. 20 billion. 20 times the current total. In one survey, running for 10 years, we'll photograph more galaxies than all previous surveys combined have photographed in the entire history of astronomy. That's transformative. That's going to completely change the field. With 20 billion galaxies catalogued, we'll have detailed enough samples to study rare objects, to understand galaxy populations with unprecedented statistical power, to trace large-scale structure across cosmic history, to detect unusual and unexpected phenomena. LSST will also monitor the sky. Because it images the same regions repeatedly, it can detect things that change. Supernovae exploding, stars flaring, asteroids moving, and galaxies changing. Though galaxy evolution happens so slowly that even over 10 years, you won't see much change in typical galaxies. But you might catch rare transient events, and the repeated observations allow you to build up deeper images by combining multiple exposures, seeing even fainter galaxies. So LSST is going to dramatically increase our count. taking us from about 1 billion catalogued galaxies to 20 billion. That's where we'll be by the early 2030 Galaxies. Beyond LSST, there are plans for even more ambitious facilities. The extremely large telescope under construction in Chile will have a 39-meter primary mirror. That's enormous, the largest optical telescope ever built. It's designed for detailed spectroscopy and high-resolution imaging. It won't survey the sky the way LSST will. Instead, it will study specific objects in exquisite detail. But it will push the distance limit. It will see fainter galaxies than any current telescope. It will reveal fine structure in distant galaxies that currently appear as mere smudges. Every galaxy the ELT observes will be photographed with unprecedented clarity. In space, there are plans for missions beyond James Webb. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Hubble. It's designed for wide-field infrared surveys. It will photograph millions of galaxies, providing infrared data that complements LSST's visible light observations. Together, these facilities will push the count of photographed galaxies even higher. Maybe by mid-century, we'll have catalogued 50 billion galaxies, maybe more. We're limited ultimately by how faint we can detect, by the sensitivity of our instruments, by how much time we can dedicate to surveys. But with each generation of telescopes, the limits expand. We see fainter, we see farther, we photograph more. The trajectory is clear. The count will keep rising. Hundreds of millions now, billions soon, tens of billions eventually. We'll never photograph all 2 trillion galaxies estimated to exist in the observable universe. But we'll photograph an increasingly large fraction, and each addition to the catalogue is valuable. Each galaxy photographed adds to our understanding, reveals new details about cosmic structure and evolution. Now let me step back and talk about what this all means, because I don't want you to get lost in the numbers. The specific count, whether it's 500 million or 1 billion or 20 billion, those are details. What matters is what they represent. Every galaxy we've photographed is a collection of billions or trillions of stars. Each star is a sun, potentially hosting planets. Some of those planets might harbor life. We don't know. We can't see individual planets in other galaxies. But statistically, given how many stars there are, life must exist somewhere in at least some of these galaxies. And we've photographed them. We've captured light from these distant collections of stars and worlds, documented their existence, created a record that says, yes, this galaxy exists. Here's what it looks like. Here's where it is. Here's how far away. That's profound. That's meaningful. It connects us to the cosmos in a tangible way. These aren't abstract concepts or mathematical models. These are photographs, visual records, evidence captured by cameras, stored on hard drives, viewable by anyone curious enough to look. You can go online right now and browse catalogs of millions of galaxies. See images from Hubble, from Sloan, from various surveys. Each one showing a real galaxy, a real collection of billions of stars, at a real location in space. It's accessible. It's real. It's not hidden knowledge, but shared heritage. And that's powerful. Consider what it means that we can do this, that we, a species that evolved on one small planet, that spent most of our history unaware that galaxies beyond our own even existed, can now photograph hundreds of millions of them, can catalogue their positions and properties, can study their structures and histories. That's an achievement worth celebrating. It's a testament to human curiosity, to our drive to understand the universe we inhabit. It's also humbling, because when you look at images of distant galaxies, when you see the sheer number we've photographed, you realize how small we are, how vast the universe is, how much exists beyond our tiny corner of space. Each galaxy we've photographed is as complex and full of potential as our own Milky Way. Each one could host billions of planets, trillions of moons, countless opportunities for complexity, chemistry, maybe life, and there are hundreds of millions we've photographed, billions more we haven't. Trillions total in the observable universe. The scale is overwhelming, but rather than making me feel insignificant, it fills me with wonder. We're part of this. We exist within this vast cosmic structure. We're made of atoms forged in stars in galaxies like the ones we photograph. We're the universe examining itself, documenting itself, trying to understand itself. And that's beautiful. That's meaningful. That gives purpose to the endeavor. Every galaxy photographed is another piece of the cosmic puzzle, another clue to understanding where we came from, what we're part of, where we're going. It's all connected. The spiral galaxy photographed by Hubble, the faint smudge detected in a Sloan survey image, the ultra-distant galaxy captured by James Webb. They're all part of the same story. The story of cosmic structure, the story of how galaxies form and evolve, the story of the universe itself. Let me also talk about the emotional and aesthetic dimension of galaxy photography. Because these images aren't just scientific data, they're beautiful, profoundly, achingly beautiful. Look at the Hubble image of the Whirlpool galaxy, the elegant spiral arms glowing with pinkish star-forming regions, the companion galaxy being torn apart by tidal forces, the intricate structure, the delicate tracery of dust lanes, the brilliant blue knots of young stars. It's art. It's one of the most beautiful images ever created. Not painted by a human artist, but captured by a camera from nature itself. Or the Sombrero Galaxy, that perfect edge-on disk with the bright bulge, the dark dust lane bisecting it, the symmetric elegance of the structure. Or the Andromeda Galaxy, our nearest large neighbor. Photographs show its grand spiral structure, its two satellite galaxies, the dense stellar nucleus, the intricate lanes of dust and gas. Knowing that this is a real object, a real collection of 1 trillion stars, makes it more beautiful, not less. Every star visible in those spiral arms is a sun, potentially hosting worlds, potentially harboring life. That adds meaning to the beauty, makes it not just aesthetically pleasing, but profound. And we've photographed hundreds of millions of galaxies, some in exquisite detail showing all this beauty and structure, others just faint smudges revealing only that they exist, that they're out there, that they're part of the cosmic population. Both matter, both contribute. The beautiful, detailed images inspire us. They appear on posters, in books, in planetarium shows. They're what draw people to astronomy. They're what make people care about distant galaxies and cosmic evolution. The survey detections, the catalogue entries, those do the scientific work. They provide the statistical samples needed to understand galaxy populations. They're the data points that let us answer quantitative questions. Both are necessary, both are valuable, and together they give us a complete picture. The detailed observations show us what galaxies look like. The survey statistics tell us how many there are and how their properties are distributed. Combine them and you understand both the forest and the trees. You see individual galaxies in all their complexity and beauty, and you see the galaxy population as a whole, how common different types are, how properties correlate with environment and cosmic epoch. This is the power of photographing hundreds of millions of galaxies. It gives us both breadth and depth, both scope and detail, both statistics and specifics, and it's all accessible. The Hubble images are publicly available. The survey catalogues are online. Anyone with an internet connection can explore them. Students can use them for projects. Amateur astronomers can browse them for pleasure. Professional astronomers can mine them for discoveries. It's democratized knowledge. Open science at its best. This openness is important. These photographs, this catalogue we've built, it belongs to humanity, not to any individual or institution or nation. It's our collective achievement and our shared heritage. The galaxies we've photographed are part of the universe we all inhabit. Documenting them, understanding them, appreciating them, that's something we do together as a species. And I find that beautiful. In a world often divided by borders and conflicts and competing interests, astronomy brings us together. We all look up at the same sky. We all wonder about the same questions. We all benefit from the discoveries made by telescopes and surveys around the world. The galaxies don't care about human politics. They exist regardless of what we think or believe, and studying them requires cooperation, data sharing, international collaboration. Scientists from every country contributing to surveys and catalogues and analysis. That's how it should be. That's how we move forward, by working together toward common understanding. And the catalogue of hundreds of millions of photographed galaxies is a testament to this collaboration. It's built from data collected by facilities in Chile, Hawaii, South Africa, Australia, Spain, space missions from NASA and ESA and other agencies. It's analyzed by astronomers from every continent, and it's shared freely with anyone who wants to use it. That's powerful, that's meaningful, that's worth being part of. Now, let me bring this toward a close by reflecting on what it means for you personally. Why should you care about any of this? You're not an astronomer. You're probably never going to analyze galaxy survey data or use these catalogues professionally. So why does it matter how many galaxies we've photographed? It matters because it changes your perspective. When you know that we've photographed hundreds of millions of galaxies, when you understand what that means, when you grasp the scale and the achievement and the implications, you see yourself and your place in the universe differently. You realize you're part of something vast. You exist in a universe containing trillions of galaxies, each one as complex as the Milky Way. Your atoms were forged in stars in one of these galaxies billions of years ago. You're the universe examining itself, thinking about itself, trying to understand itself. That's not a trivial thing. That's profound. That's what makes being human meaningful. We're the part of the universe that can photograph other parts of the universe. We're the part that can look outward and document what we see. Build catalogs, create understanding, share knowledge. That capability, that capacity for cosmic awareness, that's precious. That's rare. As far as we know, we might be the only beings in the observable universe currently doing this. There might be others, probably are, given how many planets must exist, but we don't know for certain. What we do know is that we're doing it. We're photographing galaxies, cataloging the cosmos, building a record that will outlast us. And that's meaningful. That's worth doing. So, when I tell you we've photographed 500 million to a billion galaxies, I'm not just sharing a number. I'm telling you about human capability, about what we've achieved, about what's possible when we look up with wonder and ask questions and build instruments to answer them. Every galaxy photographed represents effort, represents people dedicating their careers to building telescopes, conducting surveys, analyzing data, represents funding from governments and agencies and universities supporting this work, represents humanity deciding that understanding the universe is valuable, is worth the investment. And I think it is. I think photographing galaxies, documenting the cosmos, building this catalogue of cosmic structure is one of the most worthwhile things we do as a species. It doesn't feed anyone directly. It doesn't solve immediate practical problems, but it expands human knowledge. It satisfies curiosity. It gives us perspective on our place in the vastness, and those things have value. They make us more than just survival machines. They make us thoughtful, curious beings trying to understand reality. So yes, we've photographed hundreds of millions of galaxies, and that number is growing. Will continue to grow. Will be in the billions soon, tens of billions eventually, and every addition matters. Every galaxy photographed adds to our understanding, contributes to the catalogue, helps us see the universe more completely. That's where we are. That's what we've achieved. And it's something to be proud of, something to appreciate, something that should fill you with wonder every time you look up at the night sky and remember that behind those points of light, behind the darkness between stars, there are hundreds of millions of galaxies we've photographed and trillions more waiting to be discovered. The universe is vast, but it's knowable. We can photograph it, we can study it, we can understand it, and we're doing exactly that. One galaxy at a time, one survey at a time, one telescope at a time, building up a catalogue that documents the cosmos. That's humanity's gift to itself. That's our legacy. That's what we're leaving for future generations. A photographic record of the universe, hundreds of millions of galaxies and counting, forever preserved, forever accessible, forever part of our shared knowledge. That's what makes this matter. That's why the number is important, not just as a statistic, but as a measure of human achievement, of what we can accomplish when we decide to look up and really see what's out there. Thank you for joining me on this journey through the history and scope of galaxy photography. If this kind of exploration resonates with you, please consider subscribing. Share this with someone who might appreciate understanding how many galaxies we've actually photographed and what that achievement represents. Help build a community of people who care about cosmic perspective, who understand that we're living in an extraordinary time when we can document the universe itself through photographs. The galaxies are out there, hundreds of millions that we've photographed, billions more that we'll photograph in coming decades, trillions total in the observable universe, and we're part of the species doing the photographing, the documenting, the understanding. That's extraordinary, that's meaningful, that's worth your time and attention. So look up tonight if you can. See the stars. Remember that beyond them are galaxies, hundreds of millions we've photographed, each one containing billions of stars and potentially trillions of planets, each one part of this vast cosmic structure we're trying to understand. We've photographed them, documented them, added them to humanity's catalogue of the universe, and we're just getting started. Now, let me take you even deeper into what's coming next in galaxy photography, because the future is incredibly exciting. The Vera Rubin Observatory I mentioned, with its projected 20 billion galaxies, that's just the beginning. Let me paint you a picture of what the next few decades will bring. When LSST begins full operations, probably sometime in the mid-2020s, it will revolutionize not just how many galaxies we photograph, but how we understand them. Because LSST isn't just taking single snapshots, it's monitoring the sky. It will photograph the entire visible southern sky every few nights, over and over again. For 10 years, this repeated imaging allows something remarkable. You can watch the universe change. Now, galaxies themselves don't change much on human timescales. They evolve over millions or billions of years. But things within galaxies do change. Supernovae explode, suddenly brightening by factors of billions. Variable stars pulsate. Active galactic nuclei flicker as material falls into supermassive black holes. LSST will catch all of this. Every supernova that explodes in the 20 billion galaxies it photographs over 10 years. That's millions of supernovae, each one a chance to study stellar death, to measure cosmic distances, to understand galaxy evolution. Every variable active nucleus, every tidal disruption event where a star gets torn apart by a black hole, every rare transient phenomenon, the data will be overwhelming in the best possible way. And because LSST photographs so deeply, reaching faint galaxies that previous surveys missed, it will detect events in galaxies we've never seen before. Supernovae in galaxies billions of light years away, so distant that the galaxy itself is barely visible, but the supernova for a few weeks outshines everything else and becomes detectable. This will give us samples of cosmic explosions across the entire history of the universe. From recent events in nearby galaxies to ancient explosions that happened when the universe was young, we'll be able to trace how supernovae have changed over cosmic time, how the rate of stellar death has evolved, how the chemical enrichment of the universe has proceeded, all from photographing galaxies and watching them over time. Then there's the Nancy Grace Roman Space Telescope. Launching in the mid-2020s, Roman will do for infrared astronomy what LSST does for visible light. Wide field surveys covering huge areas of sky, but in infrared wavelengths. Infrared is crucial because it's where distant galaxies appear. Remember, the expansion of the universe stretches light. Distant galaxies emit visible and ultraviolet light, but by the time it reaches us, it's been redshifted into the infrared. To see the most distant galaxies, you need infrared capabilities. James Webb is incredible at this. Its sensitivity and resolution are unmatched, but its field of view is small. It looks at tiny patches of sky in exquisite detail. Roman will complement this. Its field of view is 100 times larger than Hubble's, 100 times. In a single exposure, Roman will photograph an area of sky that would take Hubble 100 exposures to cover. This means Roman can survey vast areas of sky in infrared, detecting millions of distant galaxies, building up statistical samples that are currently impossible. The combination of LSST in visible light and Roman in infrared will be transformative. You'll have the same regions of sky photographed at multiple wavelengths, visible light showing where stars are, infrared showing where dust is, where star formation is happening, where the most distant galaxies are. Together, they'll provide a complete census of galaxy populations, not just counting galaxies, but understanding their properties across the full range of cosmic environments and distances. Beyond Roman and LSST, there's the extremely large telescope. The ELT won't survey the sky the way LSST does. Its strength is different. It's about detail and resolution. With a 39-meter primary mirror, it will be able to resolve structures in distant galaxies that currently appear as tiny blobs. Imagine photographing a galaxy 10 billion light-years away and actually seeing individual star-forming regions within it. Seeing the spiral structure or tidal features. Seeing details that right now are impossible to observe. That's what ELT will do. It will take galaxies that appear in surveys as single pixels or small smudges and reveal their internal structure. Show what they actually look like. This will revolutionize our understanding of galaxy morphology at high redshift. How galaxies looked in the early universe. We'll see that the first galaxies weren't like modern galaxies. They were smaller, more irregular, more chaotic. We'll watch how they merged and grew and settled into the ordered structures we see today. And we'll do this not through simulations or models, but through actual photographs. Direct observations of what galaxies looked like billions of years ago. The ELT will also do spectroscopy at unprecedented detail, breaking the light from distant galaxies into spectra, measuring what elements are present, how hot the gas is, how fast it's moving, whether there are outflows driven by supernovae or black holes. All of this from observations of individual galaxies billions of light years away. This detailed spectroscopy will complement the broad surveys. LSST and Roman tell you where galaxies are and roughly what they look like. ELT and Webb tell you what they're made of and what's happening inside them. Together, comprehensive understanding. Now, I want to talk about a different kind of future, not just near-term missions, but the longer view. What happens in 50 years, in a century? If humanity continues investing in astronomy, continues building telescopes and conducting surveys. Where will we be? By mid-century, I expect we'll have photographed 50 billion galaxies, maybe 100 billion. That's a significant fraction of the total. Maybe 5% of all galaxies in the observable universe. We'll have detailed observations for millions of galaxies. Complete multi-wavelength coverage for billions. Time series data showing how things change. Statistical samples large enough to study even rare galaxy types. We'll understand galaxy evolution with a completeness that seems impossible today. We'll know how often galaxies merge, how black holes grow, how star formation proceeds in different environments, how galaxies are affected by their surroundings. All of this from photographs. From accumulated observations over decades of systematic surveys. Looking even further ahead, by the end of the 21st century, assuming continued progress, we might have catalogued 200 billion galaxies, 10% of the total. At that point, we'll have truly comprehensive samples. We'll have photographed enough that we can study even the rarest objects in meaningful numbers. Ultra-massive black holes, the most distant galaxies, the most extreme starbursts. Everything that's currently unique or nearly unique will have enough examples to study statistically. And the technology will continue improving. Detectors will become more sensitive. Telescopes will get larger or more numerous. Data processing will become more sophisticated with artificial intelligence helping to classify and analyze billions of galaxies automatically. Machine learning algorithms will find patterns we couldn't see manually. Correlations between galaxy properties that are too subtle or too high-dimensional for human analysis. The AI will be trained on the photographs, learning what galaxies look like, how they're distributed, what features matter. And then it will help us understand the data we've collected. This is already happening. Modern surveys use machine learning to classify galaxies, to separate stars from galaxies automatically, to identify unusual objects that warrant detailed follow-up. As the catalogues grow, as we photograph more and more galaxies, AI will become essential. Humans can't examine billions of galaxy images manually, but computers can. And they can do it consistently, finding patterns and anomalies that might take humans years to discover. But let me bring this back to something more immediate, something you can engage with right now, because you don't have to wait for future telescopes to explore photographed galaxies. The data that exists today is accessible. I mentioned this earlier, but let me emphasize it. Right now, you can go online and explore galaxy catalogs. The Sloan Digital Sky Survey has a publicly accessible database. You can query it. Search for galaxies matching certain criteria. Download images. See what professional astronomers see. The Hubble Legacy Archive contains every image Hubble has ever taken, tens of thousands of galaxy photographs, high resolution, multiple wavelengths, all freely available. You can download them, study them, use them for projects, or just appreciate their beauty. There are citizen science projects where you can contribute to galaxy research. Galaxy Zoo, for example, shows you galaxy images and asks you to classify them. Spiral or elliptical, smooth or featured. By having thousands of people classify millions of galaxies, The project builds reliable catalogues of galaxy morphology. And it's fun. You're looking at real galaxies, real data from professional telescopes, contributing to actual research. This democratization of astronomy data is relatively new. 20 years ago, telescope data was proprietary. Only the astronomers who took the observations could access it. Now, most data becomes public after a brief period. Anyone can use it. This openness has accelerated discovery. Researchers from small institutions or developing countries who couldn't afford telescope time can now access world-class data. Students can work on cutting-edge projects using the same data as professionals. Amateur astronomers can make real contributions. And you, listening to this, can explore galaxy photographs yourself, can see what we've captured, can appreciate the beauty and complexity of these island universes. That accessibility matters. It makes astronomy not just something professionals do, but something everyone can participate in. Even if you never conduct research, just knowing you can access these catalogues, can explore these photographs, that changes your relationship to the science. It becomes tangible, real, not abstract or distant, but something you can engage with directly. So I encourage you, go look at galaxy photographs, browse the Hubble archives, explore the Sloan data, participate in Galaxy Zoo or similar projects. See for yourself what these hundreds of millions of photographed galaxies look like. Appreciate their diversity. Some are perfect spirals, others are chaotic irregulars. Some are enormous ellipticals containing trillions of stars. Others are tiny dwarfs barely visible even in deep images. Each one is unique. Each one has its own history, its own structure, its own story. And they're all out there, all documented, all part of the photographic record we've built. Now, let me address something I haven't talked about much: the philosophical implications of photographing galaxies. Because this isn't just about collecting data, it's about how we understand our place in the universe. When Hubble first proved that spiral nebulae were galaxies, when he showed that the universe was vastly larger than anyone had imagined, it fundamentally changed humanity's perspective. We went from thinking the Milky Way was everything to realizing it was one island among countless others. That shift was profound. It made us smaller, but also more aware, more conscious of the scale and scope of existence. Every time we photograph more galaxies, every time we expand our catalogue, we're reinforcing and deepening that perspective. We're documenting the vastness, making it concrete. Not just knowing abstractly that billions of galaxies exist, but having photographs of hundreds of millions of them, having their positions catalogued, having their properties measured. This makes the vastness real in a way that abstract knowledge doesn't. You can look at a photograph of a distant galaxy and know that it's real, that it exists, that somewhere in that smudge of light are billions of stars and potentially trillions of planets, and that what you're seeing is ancient light, light that left that galaxy millions or billions of years ago, before humans existed, before the Earth was fully formed in some cases. You're looking at the past, seeing the universe as it was. That's time travel in the only way currently possible. We can't physically go back in time, but we can look back. We can photograph galaxies as they were billions of years ago, and by photographing galaxies at various distances, we're building a timeline, a visual history of the universe from the early days after the Big Bang to the present. This historical perspective is unique to astronomy. No other science can directly observe its subject billions of years in the past. Geologists study ancient rocks, but they're reading indirect evidence. Astronomers photograph the past directly. Look at a galaxy 10 billion light years away, and you're seeing it as it was 10 billion years ago. That's not inference or reconstruction. That's direct observation. And every galaxy we photograph adds to this historical record. The nearby galaxies show us the present or recent past. The distant galaxies show us the ancient past. Together, they tell the story of cosmic evolution, how the universe has changed, how galaxies have grown and merged and evolved, how stars have formed and died and enriched the cosmos with heavy elements, how structure has emerged from the nearly uniform early universe. All of this is visible in the photographs. In the catalogue of hundreds of millions of galaxies we've accumulated, it's a visual encyclopedia of cosmic history. And it's growing. With each new survey, with each new telescope, we add more chapters, more details, more depth to our understanding. This is why galaxy photography matters, not just as a technical achievement, but as a philosophical one. We're documenting the universe, creating a record that says, here's what exists, here's what we found, here's what we understand, and that record will outlast us. The galaxy photographs we've taken will be accessible centuries from now, assuming human civilization preserves them. Future generations will look at our images the way we look at Hubble's photographs from the 1920s, with appreciation for what was accomplished with the technology of the time, and they'll build on it. Take even better photographs with even better telescopes, add to the catalogue, continue the work. This continuity, this multi-generational project of documenting the cosmos, that's beautiful. It's humanity at its best, working together across time, each generation contributing, each building on what came before, moving closer to comprehensive understanding. We'll never finish. There will always be more to photograph, more to discover, more questions to answer. But that's okay. The journey matters as much as the destination, and the journey of photographing galaxies, of building this catalogue, of expanding human knowledge of the cosmos. That's a journey worth taking. That's meaningful work. That's part of what makes us human. So, when I tell you we've photographed 500 million to a billion galaxies, I'm not just reciting a statistic. I'm telling you about a journey, about where we've been and where we're going, about what we've achieved and what's still to come. The number will keep growing. Billions, tens of billions, eventually maybe hundreds of billions. Each new galaxy photographed adds to the record, contributes to understanding, brings us closer to knowing the full scope and structure of the universe we inhabit. And you're part of this by caring enough to learn about it, by taking the time to understand what we've accomplished, by appreciating the photographs and the catalogues and the decades of work that went into creating them. You're part of the community of people who know, who understand, who appreciate that we're living in an age of cosmic discovery, an age when we can photograph galaxies by the billions and use those photographs to understand the universe itself. That's the privilege of being alive right now. That's the gift this moment in history offers, and it's worth appreciating, worth celebrating, worth sharing with others who might find it as meaningful as you do. The galaxies are out there. We're photographing them, documenting them, understanding them, building a catalogue that represents one of humanity's greatest achievements. And the work continues. Every night, somewhere in the world, telescopes observe, cameras capture light from distant galaxies, data is recorded, the catalogue grows, the understanding deepens, the photographs accumulate. This is our legacy. This is what we're leaving for future generations. A photographic record of the universe, hundreds of millions of galaxies and counting, forever preserved in archives and databases, forever accessible to anyone curious enough to explore them. That's what we've done. That's what we're doing. That's what we'll continue doing as long as human civilization endures. And it's extraordinary. It's meaningful. It's worth your time and attention and appreciation. Thank you for joining me on this exploration of how many galaxies we've actually photographed. The answer is hundreds of millions now, approaching billions in the near future, with no end in sight to the growth of our cosmic catalogue. Each one matters. Each one contributes. Each one is part of humanity's ongoing effort to document and understand the universe. Look up tonight. Remember the galaxies. Remember that we've photographed hundreds of millions of them. And remember that you're part of the species doing the photographing, the documenting, the understanding. That's something special, something worth holding on to, something that gives meaning to our brief time in this vast, ancient, beautiful cosmos. Let me spend a few more moments with you here on something that I think ties all of this together. Something about the nature of photography itself and what it means to photograph galaxies specifically. When you photograph something on Earth, a person or a landscape or a building, you're capturing reflected light. Sunlight bounces off the subject and enters your camera. The photograph shows you what something looks like right now, in this moment. But galaxy photography is fundamentally different. You're not capturing reflected light. You're capturing emitted light. Light generated by billions of stars fusing hydrogen in their cores. Light that has traveled across vast distances for millions or billions of years before reaching your telescope. Every photon that hits the detector in a galaxy photograph started its journey at a specific star in that galaxy at a specific time in the past. That photon was created through fusion. It worked its way out from the star's core to its surface. It escaped into space. It traveled across the empty void between galaxies. It entered our atmosphere or was captured by a space telescope. And finally, after this incredible journey, it hit a detector and contributed one tiny piece to the galaxy photograph. Think about that for a moment. Every galaxy image is built from countless individual photons, each one with its own journey spanning millions or billions of years. The light from a distant galaxy that we photograph today left that galaxy before humans existed, before the Earth cooled, before the sun formed, and it's been traveling ever since, moving through expanding space, streaming across the cosmos at the speed of light. And now, finally, we capture it, record it, add it to a photograph. That's extraordinary. That's time travel in the most literal sense. We're capturing ancient light, recording it, preserving it. The galaxy itself has changed since that light was emitted. Stars have been born and died. The galaxy might have merged with another galaxy. Its structure has evolved. But the light we're photographing shows how it looked back then. We're creating a photographic record of the universe as it was, not as it is. When I say we've photographed hundreds of millions of galaxies, I'm really saying we've captured light from hundreds of millions of galaxies at hundreds of millions of different moments in cosmic history. We're building a time-lapse of the universe, a stop-motion animation assembled from countless frozen moments. Each galaxy photograph is one frame, and when you have hundreds of millions of frames from different galaxies at different distances, you can assemble them into a narrative. You can see how things change, how galaxies evolve, how the universe transforms over billions of years. This is unique to astronomy. No other field of study has access to direct observation spanning billions of years. And it's only possible because light travels at a finite speed, because it takes time for light from distant objects to reach us. That delay, which might seem like a limitation, is actually a gift. It allows us to see the past, to photograph galaxies as they were billions of years ago, to document cosmic history through direct observation. And every time we photograph a new galaxy, especially a distant one, we're adding another data point to this historical record, another snapshot from another moment in cosmic time. The catalogue of photographed galaxies isn't just a list of objects, it's a timeline, a visual history of the universe from shortly after the Big Bang to the present day. That's what makes this so profound. We're not just collecting images, we're documenting the evolution of everything. How galaxies form, how they grow, how they change, how the universe itself transforms over cosmic time. All through photography, through capturing light, through building a catalogue of hundreds of millions of images. I want you to really feel the weight of this achievement, because it's easy to hear large numbers and not fully grasp what they represent. 500 million galaxies, a billion galaxies. These are numbers so large they lose meaning. So let me make it concrete. If you spent 1 second looking at each galaxy photograph we've taken, just 1 second per galaxy, it would take you over 15 years to see them all. 15 years of doing nothing but looking at galaxy images, one after another, never sleeping, never stopping. That's how many we've photographed. If you printed every galaxy photograph at postcard size and laid them out, they would cover an area larger than several football fields. If you stored them all on your computer, they would require hundreds of terabytes of storage. These aren't abstract numbers. This is a real, tangible collection of images, each one showing a real galaxy, each one captured by real telescopes, each one analyzed by real astronomers, each one contributing to real understanding. And this collection exists right now in archives and databases around the world, accessible to anyone curious enough to explore it. You could spend the rest of your life studying these galaxy photographs and never see them all, never exhaust the information they contain, never finish learning from them. That's how rich the resource is. That's how much we've accomplished. But despite this enormous catalogue, despite having photographed hundreds of millions of galaxies, we've barely started. Remember, there are about 2 trillion galaxies in the observable universe. We've photographed maybe 0.5%, maybe 1% if you count generously. 99% remain unphotographed, undocumented, unknown beyond statistical inference. This should humble us, should remind us how much we don't know, how much remains to discover. But it should also excite us, because it means the journey is just beginning. The catalogue will keep growing, the surveys will continue, the telescopes will improve, and centuries from now, assuming humanity survives and thrives, our descendants will have photographed billions or tens of billions of galaxies. They'll have documented a significant fraction of the cosmic population. They'll have a photographic record of the universe that's comprehensive in ways we can barely imagine. And they'll build on what we've done. They'll use our catalogues as foundation. They'll look at our images the way we look at early 20th century photographs, with appreciation for what was accomplished, but also awareness of how much better their instruments are, how much more they can see. This continuity, this building across generations, that's what great science looks like. No single generation finishes the work. Each contributes, each pushes the boundaries, each adds to the catalogue, and together, across centuries, we build comprehensive understanding. We document the universe. We photograph galaxies by the billions. We create a record that will outlast any individual, any institution, any nation, a record that belongs to humanity, that represents our collective effort to understand the cosmos we inhabit. Now let me end by bringing this back to you personally one more time, because I don't want you to walk away from this thinking it's just interesting trivia. I want you to understand how this connects to your life. You exist in a universe containing trillions of galaxies. Most you'll never see, most will never be photographed, but hundreds of millions have been. We've captured their light, documented their existence, measured their properties, and in doing so, we've learned about where you came from. The atoms in your body were forged in stars. Those stars lived in galaxies. Some of those galaxies we've photographed. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it was created in stellar cores through fusion. Then those stars died, some in spectacular supernovae, scattering their enriched material into space. That material became part of new generations of stars and planets. Eventually, it became part of you. You're made of recycled stardust. Material that was once inside stars in galaxies, we can now photograph. That connection is real. It's not metaphor or poetry, it's literal physical history. And photographing galaxies helps us understand that history, helps us trace how elements are created and distributed, how generation after generation of stars lives and dies, enriching the cosmos, how that enrichment makes complex chemistry possible, makes life possible, makes you possible. So when we photograph galaxies, when we add to this catalogue of hundreds of millions, we're not just doing abstract science. We're learning about ourselves, about where we came from, about what we're made of, about how the universe evolved to the point where beings like us can exist and wonder and ask questions. That's meaningful. That's personal. That's why you should care about how many galaxies we've photographed and what we learn from those photographs. Because it's your story too. You're part of this cosmic narrative, made of atoms forged in distant galaxies. Living on a planet orbiting a star in a galaxy we've definitely photographed. Looking out at hundreds of millions of other galaxies and trying to understand them. Trying to understand yourself in the process. That's the gift of astronomy. That's what galaxy photography gives us. Not just pretty pictures or interesting data, but connection, understanding, perspective on who we are and what we're part of. And we're living in the golden age of this. Right now, more than at any point in history, we can photograph galaxies. We can see them in exquisite detail. We can study them systematically. We can build comprehensive catalogues. The telescopes exist. The technology works. The data is accumulating. And it's all happening during your lifetime. That's not something to take for granted. That's a privilege, a gift, an opportunity to participate in one of humanity's greatest projects. Even if you never become an astronomer, even if you never use the catalogs professionally, just knowing they exist, knowing what we've accomplished, knowing how many galaxies we've photographed, that changes how you see the world. It should make you feel connected to something larger, part of a species that looks up and wonders and builds instruments to answer cosmic questions. That's worth celebrating, worth appreciating, worth sharing with others. So here's what I want you to do. Tonight or soon, find a dark place. Look up at the stars. Let your eyes adjust. See the Milky Way if you're somewhere dark enough. That band of light across the sky, that's our galaxy seen from inside. Billions of stars blending together. Now remember that beyond what you can see with your eyes, beyond the stars visible in the night sky, there are hundreds of millions of galaxies we've photographed, each one containing billions of stars, each one as complex and vast as the Milky Way. And we've documented them, captured their light, added them to humanity's catalogue of the universe. That knowledge, that awareness, should change how you feel looking up at the night sky. Should make it feel more vast, more full, more meaningful. You're not just seeing stars. You're seeing the edge of something incomprehensibly large, and we're exploring it. We're photographing it. We're understanding it, one galaxy at a time. That's the answer to the question I posed at the beginning. How many galaxies have we actually photographed? The answer is hundreds of millions. Between 500 million and approaching 1 billion, depending on how you count. With billions more coming in the next few decades. Each one a triumph of observation. Each one a contribution to human knowledge. Each one part of the photographic record of the universe that we're building together as a species. And it's growing. Every night, telescopes observe. Every day, data is processed. Every week, new galaxies are added to catalogs. The number I've given you is already out of date. It's higher now than when I started talking. It will be higher still tomorrow, higher next week, higher next year. The catalogue never stops growing, and neither does our understanding. With each new galaxy photographed, we learn something. Maybe just a small increment, maybe a revolutionary discovery, but always forward, always adding to the sum total of human knowledge. This is what we do. We photograph galaxies, we document the universe, we build catalogues that will outlast us. We contribute to a multi-generational project of cosmic understanding, and we do it because we're curious, because we wonder, because we want to know what's out there. That curiosity, that drive to explore and understand, that's one of the best things about being human. And galaxy photography is one of its purest expressions. Looking up, wondering what those distant lights are, building telescopes to see them better, capturing their light, studying them, understanding them. That's beautiful, that's meaningful, that's worth dedicating resources and careers and lifetimes to. And the result is this extraordinary catalogue. Hundreds of millions of galaxies photographed, documented, available for study, growing every day, approaching billions in the near future, tens of billions eventually. A photographic record of the cosmos that represents one of humanity's greatest achievements. Thank you for taking this journey with me, for caring enough to learn about how many galaxies we've photographed and what that means. If this resonated with you, if it changed how you see the universe even slightly, please share it. Tell others. Help build a community of people who appreciate cosmic perspective, who understand that we're living in an extraordinary time when we can photograph galaxies by the hundreds of millions and use those photographs to understand our place in the cosmos. The galaxies are out there, we're photographing them, and that's something worth being part of, something worth appreciating. Something that makes being human, being alive right now, in this moment of history, truly special. Look up tonight. Remember the galaxies. Remember that we've photographed hundreds of millions of them. And remember that the work continues. The catalogue grows. The understanding deepens. And we're all part of it. That's the gift. That's the privilege. That's what makes this matter. How many galaxies have we actually photographed? Hundreds of millions and counting. And every single one matters.